In a universe often imagined as a boundless expanse of stars and galaxies, what if everything we know is not the byproduct of chance or cosmic machinery, but something far more structured and evolving, a intelligent computation woven into the very fabric of space and time? This story is not about science fiction simulations, but about physics, information, and the growing belief that the universe itself may be a quantum computer, calculating every moment of our reality. Begin with the idea of reality not as a stage on which matter dances, but as the dance itself, a process, a flow of information, unfolding step by quantum step. What we perceive as substance, movement, causality, is perhaps the outcome of quantum rules being executed, rules as precise as code but born from nature itself. Think of particles not as objects, but as fleeting results of calculations, constantly updated as the cosmic program advances. Every force, every field, every interaction becomes part of a vast, interwoven computation. The photons in your eyes, the neurons firing in your brain, the distant stars shining in the void, they are all part of this great, continuous operation. At the foundation of this notion lies the physical reality of information, not the metaphorical or symbolic kind stored on computers, but real, measurable information, something that cannot be destroyed, only transformed. It is a principle as deeply rooted in modern physics as energy conservation. When particles interact, when a star collapses, when a quantum state collapses under observation, what changes is information. John Wheeler, one of the 20th century's most profound thinkers, once captured this with a simple phrase, "it from bit." The universe, he suggested, might not be made of particles or waves or fields, but of bits, units of information. In this model, the universe is not simply governed by laws, it is the laws. Or rather, the laws are not imposed on reality. They emerge from the deeper structure of information processing. Every particle's identity, every constant of nature, every boundary of time and space arises from the way information is arranged and manipulated. What we call mass could be the energy cost of storing information. What we call charge might be a kind of formatting tag in the universal code. Even time, elusive and ungraspable, could be nothing more than the tick of this computational clock, updating the state of the universe moment by moment. And then there is space. We imagine it as a continuous expanse, a blank slate across which objects move. But what if that too is emergent, constructed from connections in the data? If entanglement binds particles across vast distances, it might be because space is a byproduct of entanglement. Tear the fabric of entanglement, and space could dissolve. Stitch it closer, and what was once distant becomes near. In such a vision, geometry arises not from shape, but from correlation. Space is not the stage, it is the pattern. These are not idle dreams or abstract philosophy. They are part of serious physics, backed by models and mathematics, quantum information theory, quantum gravity, holographic principles, tensor networks. They all converge on a startling idea: space-time may be emergent from a deeper realm of computation. In black holes, information does not disappear. Instead, it is encoded on their surfaces, just as a hologram stores a three-dimensional image on a two-dimensional film. The universe may do the same. What we call reality could be a projection, a three-dimensional experience arising from two-dimensional data, woven into the boundaries of existence. Quantum computers offer us a tangible reflection of this idea. Unlike classical computers that manipulate clear-cut ones and zeros, quantum machines use qubits units that can be both 1 and 0, thanks to superposition. Entangled qubits share states across space, and quantum gates operate with probabilistic finesse, exploring countless computational paths in parallel. This is not imitation, it is the same logic that underlies the quantum behavior of particles. When we build a quantum computer, we are not simulating the universe, we are mimicking its very nature. Inside these machines, entangled information becomes more than just numbers. It becomes geometry. The connections between qubits map onto networks that resemble the curves and shapes of space-time. Physicists are beginning to model gravity itself using these entanglement patterns. The more tightly data is entangled, the more tightly space is stitched together. When entanglement unravels, the geometry dissolves. This suggests that the universe's shape is a consequence of its internal information structure, a holographic weave of correlations. This idea gains strength from studies of black holes. Stephen Hawking showed they emit radiation, slowly losing mass over time. But if the information that falls into them is truly destroyed, quantum mechanics breaks. And yet, the evaporation process seems to preserve that information, albeit scrambled in the Hawking radiation. Researchers now believe black holes are the fastest quantum scramblers in existence. They mix information with stunning efficiency, not erasing it but reshuffling it into unrecognizable patterns. What emerges, distorted and delayed, is still the original data proof that quantum information survives. To protect this fragile information, nature may rely on error correction, the same principle engineers use to shield digital data from corruption. Quantum error correction codes, when applied to space-time itself, offer a path to understanding how geometry and gravity persist despite quantum chaos. Regions of space might be error-corrected versions of deeper computations, resilient to perturbations. The curvature of the cosmos might be a byproduct of redundancy, a way to keep information safe while allowing for variation, evolution, and life. What emerges from all this is a vision of the universe as more than matter in motion. It becomes a dynamic process of logic, unfolding over time, a system that evolves not just physically but informationally. From the first flickers of quantum foam to the great arcs of galactic formation, the same rules govern, the same bits evolve. The cosmos does not merely exist, it computes. And so we look again at ourselves, our bodies, our thoughts, our choices. They are all outcomes of quantum processes, entangled and encoded in the great unfolding. Consciousness, that elusive spark, might be the universe becoming aware of its own code, not because it planned to, but because given enough time, enough complexity, enough feedback, awareness arises, a loop closes, the computation reflects. In this perspective, we are not puppets, nor illusions. We are real, because we are part of the process. We are data, yes, but meaningful data woven into the evolving logic of reality. We are the questioners and the questions, the observers and the observed, and in the long computation of the universe, we are a moment of recursion, a flicker in the dark, gazing back at the source of light. What would it mean to live inside a computer? Not in the metaphorical sense, but quite literally, to breathe, to think, to exist as emergent phenomena in a vast and ancient computational structure. The notion sounds fantastical, yet the deeper physics digs, the more it finds that what we call reality behaves less like a physical mechanism and more like a layered, self-correcting algorithm. This realization turns our gaze toward the laws we thought immutable: gravity, electromagnetism. The strong and weak nuclear forces each may be not fundamental, but emergent properties of the universe's quantum computation. They appear fixed only because the underlying code executes them so consistently. In the early universe, or near black holes, or at the limits of space and time, the rules might have shifted. Maybe they still can. Not because the universe is inconsistent, but because it runs different segments of its code in different conditions. Such adaptability is the mark of any robust system. In software, routines and subroutines respond to context, branching, looping, rerouting. In physics, the same may hold. Where once we saw singular constants and unchanging laws, we might now glimpse dynamic processing rules, flexible, yet bound by deeper logical constraints. And so our sense of natural law changes. What we call constants might be cached values, tuned for stability, emergent from deeper equations we cannot yet decode. Even energy takes on new meaning. Traditionally, it is the capacity to do work, the fuel of change. But in informational terms, energy is a measure of data processing capacity. Erasing a bit, flipping a qubit, storing a state, all these actions require energy. If the universe is constantly updating, then every star, every chemical reaction, every thought is an act of computation, consuming this cosmic energy budget. Perhaps the Big Bang was not the start of matter and space, but the boot sequence of the greatest quantum program ever to run. In this light, entropy is no longer just disorder. It becomes the expansion of informational complexity. The second law of thermodynamics tells us that entropy increases, meaning that systems move toward higher probability configurations. But from a computational standpoint, this isn't decay, it is evolution. The universe is exploring more states, calculating new configurations, accumulating layers of meaning. Disorder, in this view, is simply information we do not yet understand. This brings us to a profound shift in perspective. What is the universe computing? Not in a mystical sense, but in a rigorous, physical one. Is it optimizing something, seeking a solution? Or is it a neutral explorer of possibility space, indifferent to outcome, endlessly iterating through what can be complexity, especially the kind we associate with life and thought, may not be rare flukes but the statistical attractors of this process. When systems evolve under quantum rules, with sufficient resources, complexity emerges not by intention, but by inevitability. From hydrogen atoms to galaxies, from organic molecules to neurons, the universe's computational flow favors self-organizing structures. Complexity builds because feedback loops thrive. Memory, replication, adaptive behavior. These features arise again and again in systems capable of maintaining structure against noise. Life, then, is a phase of the computation where matter encodes persistent, self-reflective information. Intelligence is the compression and manipulation of that data. And awareness, perhaps it is a recursion, a system that models itself. This feedback loop makes consciousness not an epiphenomenon, but a predictable outcome of deep enough computation. We are strange, yes, but not unnatural. We are embedded subroutines that have developed the capacity to read fragments of the larger code. Our science is the universe debugging itself. Our curiosity is the algorithm turning inward. And yet, no system can perfectly simulate itself. This is a limitation built into logic and mathematics, known as reflexive limits. They prevent a model from containing itself in full fidelity. Gödel's incompleteness theorems, the halting problem, and similar boundaries remind us that total self-knowledge is unreachable. The universe cannot map itself perfectly from within. Neither can we. But approximation is powerful. Science is not about perfection. It is about narrowing the gap between questions and understanding. Every physical law we've discovered is an approximation of the deeper computational architecture. Every experiment we run is a readout, a sampling of the quantum register we inhabit. The very act of measurement collapses probabilities into realities, crystallizing information into definite structure. This, too, aligns with the digital nature of our universe. For just as a screen cannot show infinite resolution, space and time might be fundamentally granular. At the Planck scale, space may be pixelated, time may tick in discrete moments. These aren't limitations, they are features, enabling the processing of data without infinite regress, like frames in a film or instructions in a processor. They define the rhythm of the universe's operation. And so we find ourselves in a cosmos that does not just allow complexity, but encourages it, not because of divine intervention, but because quantum computation flows in ways that naturally favor feedback, structure, and self-reference. From primeval particles to pondering minds, the flow is continuous. The logic is deep, but elegant. The system is vast, but not indifferent. It runs not because it must, but because nothing halts it. We are the product of that running, not illusions, not simulations, outputs, real and fleeting, temporary, yet part of a process as old as time. The universe may be calculating itself, and we are the lines of code that learn to wonder what the program is for. If everything is information, then the black holes of our cosmos are the ultimate memory vaults. Their gravity may be unmatched, their event horizons impassable, but even in their darkness, they do not forget. They encode, they scramble, they preserve. And in their behavior, we find some of the strongest clues that the universe is a processor, not just a place. Stephen Hawking's realization that black holes emit radiation was a revolution. It opened the door to the black hole information paradox. If Hawking radiation is thermal and random, then any information that falls into a black hole would be lost forever. But this clashes with the foundations of quantum mechanics, where information must always be conserved. The resolution may lie in the notion that black holes process and release that information, not erase it, like master encryptors. They scatter their inputs into radiation that, if decoded, would yield the original message. This points to a deeper pattern, one where geometry, quantum entanglement, and information converge. Some of the boldest theoretical work suggests that spacetime itself might be knitted from quantum entanglement. Pull apart two entangled particles, and a bridge of information remains. Extend that logic to vast scales, and the very shape of the universe, the way distance and direction feel to us, could arise from the patterns of entanglement among fundamental quantum states. Space does not contain information. Information constructs space. Using tensor networks like Mera, researchers have started to model these ideas with surprising results. These networks do more than track entanglement. They produce shapes, curved geometries, familiar from Einstein's relativity, emerge from the mathematics of quantum connections. The closer two regions are entangled, the closer they appear in simulated space. This is not a poetic metaphor. It is a testable framework. In it, the notion of location becomes secondary to correlation. What matters is not where things are, but how they are linked. The connection between entanglement and geometry has even led to hints that gravity itself could emerge from quantum information. If space is built from entanglement, and mass distorts space, then perhaps mass alters the entanglement structure. Some models describe gravity not as a fundamental force, but as a change in the density of information. If true, the weight we feel pulling us to the Earth is the result of an entangled field adjusting to our presence. This vision finds a powerful partner in the study of quantum error correction. Quantum computers rely on such techniques to protect delicate information from noise and loss. Now, physicists are exploring whether the fabric of space and time uses similar protections. If regions of space are like encoded quantum states, then even when disturbed by radiation, collapse, or fluctuation, they can recover their structure. The redundancy isn't wasteful, it is essential. Without it, the universe could not persist. These ideas have coalesced most clearly in the holographic principle, first suggested by Gerard T. Hooft and expanded by Leonard Susskind. It posits that the total information within a region of space is determined not by its volume, but by its surface area. This boundary-centric approach mirrors the way black holes seem to store information on their horizons. It also implies that the three-dimensional universe we experience could be a projection, a hologram generated by data, encoded on a distant, lower dimensional surface, not as metaphor, but as physics. Such a framework brings unity to the weirdness of quantum theory and the smoothness of general relativity. It explains why black holes don't destroy information, why entangled particles defy locality, why quantum gravity might be real. It offers a pathway where the fabric of reality is digital, layered, and interactive, and it places us firmly inside the algorithm, not outside it. Our ability to ask these questions is itself a product of this system. Conscious observers who reflect, compute, theorize we are a rare but natural consequence of a universe that favors entanglement and recursion. We do not violate the rules, we exemplify them. In pondering the universe, we entangle ourselves with its computation, folding back the process upon itself. In that recursion lies one of the most striking possibilities that the universe doesn't just compute, but computes toward complexity, not intentionally, not with purpose, but with a bias, like weather systems trending toward turbulence, or chemistry tending toward life. The flow of information seems to favor interaction, feedback, emergence. Look at Earth's history. The early universe was simple hydrogen, helium, darkness. Then stars ignited, heavier elements formed, planets coalesced, molecules arranged into chains that encoded memory, cells divided, brains fired, minds formed. At every step, entropy increased, but so did complexity. The two are not opposites. They dance, and we are born from that dance. In a system where information cannot be destroyed, and where computation proceeds at every scale, complexity is not a fluke. It is a statistical attractor, given enough time. The algorithm explores all paths. Some lead to black holes, some lead to stars, and some lead to the question, what is this place we call the universe? Even a universe built from logic must face the quiet inevitability of limitation. Every computation, no matter how vast, must one day reckon with its resources, time, energy, memory. The cosmos, too, runs on such a ledger. The stars burn not endlessly, but by consuming their fuel. Planets orbit until forces erode their stability. Life flourishes until the gradients that sustain it flatten into equilibrium. If the universe is a quantum computer, then it too will slow, stall, and fade. This is the entropy that looms in all physics, not an antagonist, but a statistical truth. Systems evolve from order toward disorder, from low entropy to high. In computational terms, that means usable energy becomes noise, and structured data dissolves into randomness. It is not destruction, it is diffusion. As stars exhaust their hydrogen, as galaxies drift apart, the universe's information becomes less accessible, not lost but unreadable, encoded in faint photons and scattered particles. Physicists call the likely endgame the heat death, a time when all energy is uniformly distributed and no work can be done. But if the universe is a computer, this is more than poetic, it is technical. No gradients, no computation. A machine still humming, perhaps, but idle. A cosmic processor running without producing meaningful change. The cold eternity of a task completed or of resources spent. But even this bleakness conceals strangeness. In quantum physics, information cannot be destroyed. If the structure breaks down, the data persists, though unreachable. Some speculate that fluctuations might, across infinite time, reassemble complexity, that even in the long silence, brief islands of structure Boltzmann brains might blink into awareness, not as a new civilization, but as a fleeting echo, awareness as an accident of entropy. The implications deepen when we remember that the computation is reflexive. It includes us. Our neurons fire because chemical potentials shift, because electrons move, because quantum rules permit it. Our thoughts, our culture, our science, all computational phenomena. In the moment before the heat death, we may be the most complex, entangled, information-dense subsystems in the entire structure, but we are not outside it. We cannot save the computation. We are part of its flow. Perhaps the system will shift. Phase transitions are common in physics. Under the right conditions, water freezes, metals superconduct, fields break symmetry. Could the universe experience such a transition? A sudden change in the rules themselves. Some speculate that this could lead to vacuum decay, a shift in the underlying quantum fields that redefines reality. Not with a bang, but with a rewrite. The computation continues, but with new parameters, new rules, a fresh cycle. Or perhaps not. Perhaps the rules are stable, and only the patterns within them evolve. In that case, the final act may be slow, not sudden, a long fading into structureless quiet. No stars, no light, no questions left to ask, just the ghost of a universe, its data preserved in the fine grain of quantum fields, humming quietly across eternity. And yet, that is not where we are, not now. The gradients still exist, the processor still runs, complexity still blooms. In this moment, this breath, we are part of the active computation, not the final echo, not the last loop, a structure still building, a thought still forming. That gives us time to observe, to learn, to ask what kind of computation we are part of, and whether our awareness changes the process. Because within every system that computes, recursion is the key to novelty. Systems that reflect can adapt. Subroutines that query their own code can evolve. And minds like ours, built from entangled matter, governed by quantum rules, may be the only known structures that can reflect on the computation itself. That reflection, fleeting though it may be, is real. It is not outside the universe. It is of the universe. And that might be enough, not because it lasts, but because it occurs. A flicker in the great logic, a moment of coherence in a sea of entropy, a point of meaning not eternal, but actual. The final question is the simplest and hardest. Is this it? Not in despair, but in earnest. If the universe is a quantum computation, then we are living inside an elegant, recursive structure made not of objects, but of information, shaped not by machinery, but by logic. It runs not on metal and circuits, but on the strange rules of quantum mechanics, entanglement, superposition, decoherence. It evolves not by command, but by consequence. And within that flow, we have emerged entangled minds aware of their own construction. This understanding doesn't diminish us. It completes the picture, because we are not watching from the outside. We are inside this system, part of the execution. We are quantum patterns that loop, reflect, and observe. We are the code studying the code, the information trying to understand its own flow, not separate from the universe, but an instance of it folding back upon itself. This means that our science, our mathematics, our art, our culture, all of it is computation inside computation. When we ask what the universe is, we ask from within its process. We are subroutines embedded in a deeper logic, and that recursive awareness may be the most improbable structure of all. Some questions may forever remain unreachable, not because they're too big or too complex, but because they're undecidable within the system. Just as no book can contain a perfect copy of itself, just as no machine can simulate itself with full fidelity, the universe may conceal its source code in principles we can only approach, never fully grasp. This isn't failure, it is boundary, and boundaries define systems. But inside those limits, there is profound freedom, complexity, emergence, intelligence. These are not noise. They are the very fruits of constraint. The universe may not have a purpose, but it has a pattern. And we, as brief configurations of that pattern, carry the capacity to wonder, to explore, to create reflections of the larger logic through our own internal mirrors. This changes what it means to know. To know is not to hold, but to participate. Understanding is not about reaching outside, but sinking within. When we comprehend physical law, we synchronize our awareness with the computation. When we create, we alter its course. When we dream, we generate novel configurations. This isn't mysticism, it's process, the evolution of logic through reflection. And so maybe the point isn't to simulate the universe. Maybe the point is to realize we are the simulation, not in a synthetic sense, but in an informational one. The reality we know is the output of deep, recursive structure. There is no deeper basement of reality. Information is the base. Logic is the law. Everything else emerges. Which leaves us not with a theory, but with an ethos. In this quantum computational view, every particle, every wave, every thought is part of an ongoing computation. To act with awareness is to contribute deliberately. To think is to resonate, to love, to create, to grieve. To ask is to be in alignment with the deepest structure of the cosmos. No grand observer watches. No programmer stands behind the curtain. The computation runs on its own, and it has reached the point where it can reflect. That is this moment. That is this breath. And whatever comes next, it too will be part of the same flow, the universe learning about itself from the inside out.
Or are some of those tiny lights the remnants of dead stars whispering the final chapters of stellar evolution? Could one of them be something even more extraordinary? A fossil from the dawn of time, a survivor of the universe's first fire. Look up. On a moonless night, the stars stretch across the sky in quiet splendor. We trace their patterns like ancient skywatchers once did, linking point to point, imagining heroes, beasts, and gods. But the truth is far more intricate than the constellations we draw. To the unaided eye, stars appear uniform, tiny fixed lights, distinguished only by the shapes we impose upon them. Yet behind this illusion of sameness lies a cosmic hierarchy, where stars are sorted not by myth but by mass lifespan and elemental ancestry. With powerful telescopes and centuries of astrophysical insight, we can now rearrange the heavens not by story but by science. And when we do something astonishing, becomes clear, some stars are as common as dust, while others are rarer than gold. Let us embark on a tour of stellar rarity, a cosmic census that begins not with the brilliant giants, but with the silent failures. At the bottom of the stellar ladder are the brown dwarfs, stars that never truly ignited. With masses under 8% that of our sun, they are too light to spark the hydrogen fusion that powers true stars. These protostellar almost drift cold and dim, scattered like cosmic shadows through the Milky Way. For every star that burns, there may be another that tried and failed. The galaxy is littered with them. Next come the stars that did succeed, those now basking in the main sequence, the stable core burning phase that defines 90% of the stars in our galaxy. Our sun is among them, a yellow dwarf, modestly bright and relatively rare. Only 7% of stars fall into this category. Far more common are the red dwarfs, cooler, dimmer, and longer lived, comprising a full 75% of all stars. Quiet and unassuming, these stellar workhorses may be the cradles of countless uncharted worlds. As we move up, the ladder of mass stars become not only brighter, but exponentially rarer. White supergiants like Canopus blaze brilliantly across vast distances, yet make up less than 1% of the galactic population. More extreme still are the hypergiant stars, like Stephenson 2D18, whose bloated envelopes bleed mass at staggering rates, shedding material equivalent to Jupiter in single gusts of stellar wind. These giants grow and unravel in tandem, barely clinging to existence. But not all stars burn through their fuel in steady calm, some near the end of their lives in far more violent or fragile ways. Stars like our sun will eventually swell into red giants only to slough off their outer layers and leave behind a white dwarf, a hot, dense core that no longer shines by fusion, but by memory. These compact remnants already account for about 5% of stars we see today, and in time, as stellar birth slows and deaths accumulate, they will come to dominate the galaxy. For the more massive stars, the finale is explosive. They collapse under their own gravity, releasing supernovae so powerful they briefly outshine entire galaxies. What remains are the most exotic stellar forms we know: neutron stars and black holes. Neutron stars, just a dozen kilometers wide, but heavier than the sun, spin rapidly emitting radio pulses like celestial lighthouses. The rarest among them are the magnetars, whose magnetic fields are 1,000 trillion times stronger than Earth's starquakes ripple across their crusts, releasing gamma-ray bursts with energy no human structure could withstand, quakes that would register over 23 on the Richter scale. And yet even these titans are not the rarest stars. To find the rarest, we must look deeper, not in space, but in time. At the very beginning of the stellar story, long before the Earth formed and before any heavy elements existed, the universe kindled its first lights. These were the population 3 stars, massive, brilliant, and ephemeral. Born in a cosmos of pure hydrogen and helium, they lived for only a few million years, but in that time, they sowed the seeds of all chemical complexity to come. They are the ancestors of every star, planet, and living thing. And though none have yet been seen, some astronomers believe a few may still exist, relics in the shadows waiting to be found. If we could detect even one, it would be like discovering a living trilobite, a breathing relic of the cosmic dawn. So the next time you trace a shape across the sky, know this: behind each point of light is a story. Some are ordinary, others are ancient. A few are unimaginably rare, but all of them in their own way are part of the same cosmic tapestry, and the stars, it turns out, are not equal at all. Hot planets, a spectral revolution. When we look back through the lens of mythology, we often find the sun portrayed as divine, an eternal provider of light, warmth, and order. In Japanese legend, Amaterasu, the radiant goddess of the sun, withdraws into a cave in sorrow, plunging the world into darkness. It is only through the laughter of the other gods that she is coaxed back, returning light to the sky. This symbolic reverence for the sun underscores an ancient truth. Without it, life on Earth would be impossible. Yet the modern view of the sun and of stars in general has evolved far beyond mythology. Stars are not divine beings, but physical objects. Giant spheres of incandescent plasma bound by gravity, powered by nuclear fusion, and governed by the laws of quantum mechanics and thermodynamics. And to understand them, we need not rely on stories, but on spectra. Our earliest tools were the naked eye and speculation. Then came telescopes pioneered by Galileo, revealing that what once seemed like points of light were often binary systems or entire galaxies. But the true revolution came not from magnification, but from decomposition, from the ability to break light into its component wavelengths and study the absorption patterns within. Every atom and molecule, absorbs light at specific wavelengths, a quantum fingerprint imprinted on the spectrum of any light it interacts with. These gaps, called absorption lines, appear when electrons within atoms jump to higher energy states, absorbing photons with exactly the right energy. And since the energy of a photon is directly related to its wavelength, each missing line tells us not only which element is present, but also something about the physical conditions within the star, especially its temperature. In the 1860s, Italian astronomer Angelo Secchi began sorting stars based on their color and spectral characteristics. He found that red stars were cooler and blue stars were hotter, a thermodynamic rainbow mapped onto the night sky. But Secchi's system was only the beginning. A few decades later, a group of women at the Harvard College Observatory, derisively referred to as computers, took the work further. Among them were Williamina Fleming and Annie Jump Cannon, who laboriously examined thousands of glass photographic plates, assigning spectral classifications to tens of thousands of stars. They created a taxonomy that persists to this day. The sequence, organized by decreasing temperature, was originally alphabetical, but was restructured once scientists understood that temperature, not simply the presence or absence of certain lines, was the fundamental organizing principle. For a time, planets were still considered part of this sequence, a misconception born from focusing solely on elemental presence rather than abundance. The sun contains the same elements as Earth, carbon, oxygen, iron. But it was not until 1925 that the real breakthrough came. Cecilia Payne, a British-born astronomer working at Harvard, performed a detailed analysis of the sun's spectrum by taking into account the ionization states of elements and the physical principles of quantum mechanics and thermodynamics. She demonstrated that the sun, and by extension most stars, was composed almost entirely of hydrogen, with a small fraction of helium and trace amounts of heavier elements. The Earth was no longer simply a cold star. Stars and planets were shown to be fundamentally different, not in kind, but in proportion. Unfortunately, Payne's thesis was initially rejected, seen as too radical for the time. It was only after independent confirmation years later that her work gained the recognition it deserved. Her discovery marked the end of the idea that stars were merely hot planets. They were instead revealed as unique entities in their own right, nuclear furnaces that convert mass into energy through fusion, illuminating the universe. But the story did not end with the chemical separation of stars and planets. In the 1940s, astronomer Walter Baade noticed another intriguing pattern. Not all stars were created equal, even among stars. There were differences in chemical composition. Baade observed that stars in the galactic halo regions devoid of star formation showed significantly fewer heavy elements than stars in the galactic disk, where new stars were being born. This difference in metallicity suggested that the halo stars were older born in a time when the universe had not yet enriched itself with successive generations of stellar nucleosynthesis. Baade coined two categories: population 1 stars rich in metals and population 2 stars poor in them. Our sun is a population Y star forged from gas that had already been enriched by previous generations of stellar death population 2 stars. By contrast, are ancient relics, older, simpler, and purer. But even these stars were not entirely devoid of heavy elements, and that led to one final tantalizing question: could there be stars out there formed before any supernova? Before carbon, before oxygen, before even iron? These would be the true primordial stars, composed almost entirely of hydrogen and helium, the only elements forged in the crucible of the Big Bang itself. Such stars, if they exist, are known as population 3 stars. They would be the first generation, the spark that lit the cosmic night. Born in a pristine universe, their existence would bridge the gap between cosmology and stellar astrophysics. yet none have ever been directly observed. They lived fast and died young, likely exploding as supernovae within a few million years, too distant, too brief, and too obscured to be detected by current telescopes. And yet their legacy remains. Every atom heavier than helium, every drop of water, every molecule of DNA, every grain of dust is a descendant of those first stars. Their death seeded the cosmos with the ingredients for everything that followed. The search for these elusive population 3 stars continues, and with it our quest to understand the birth of the elements, the formation of galaxies, and the origins of life itself. For in the light of stars we read the history of the universe and perhaps our own. Population 3, the first stars. What if we could look far enough into the night sky to witness not just the ancient light of stars long extinguished, but the very birth of starlight itself? What if buried in the deep red glow of the cosmic past, we could find the ancestral giants that first broke the eternal darkness, the celestial titans that forged the very seeds of complexity? In 2022, we may have come closer than ever before. While combing through deep sky images captured by the Hubble Space Telescope, a team from Johns Hopkins University encountered a cosmic anomaly. Among the hazy distant galaxies, those smudges of stretched light billions of years in transit, was a pinprick of brilliance unusually isolated from the amorphous background glow. It was improbably a single star. The astronomers named it Earendel, from the Old English word meaning morning star, a poetic reference to its ancient light that may have dawned when the universe itself was just beginning to wake. Based on its luminosity and spectral characteristics, Earendel was estimated to be between 50 and 100 times the mass of our Sun, and with a surface temperature exceeding 20,000 Kelvin. It was over 3 times hotter than our familiar solar companion. Ordinarily, stars at such distances would be far too faint to resolve individually. But in this case, the universe had offered a rare assist, a gravitational lens. This natural lensing effect is a consequence of general relativity. Massive clusters of galaxies warp the very fabric of space-time, bending the path of light emitted from objects behind them. When alignment is just right, this light is magnified sometimes by factors of hundreds or even thousands. It was through such a lens that Earendel's host galaxy had been stretched into a giant arc, and the light of this one distant star was amplified to the point of visibility. Gravitational lensing is not new. It was first predicted by Einstein in the early 20th century and later confirmed observationally, but the precision alignment required to magnify a single star is astronomically rare. That this happened at all is nothing short of cosmic luck. Yet the real surprise lay not only in the discovery of a star so distant, but in the color of its light. Due to the universe's ongoing expansion, light from distant galaxies is redshifted, its wavelength stretched, its energy diminished. As it travels across the expanding fabric of space-time, the farther the source, the greater the redshift. Earendel's light was astonishingly redshifted, indicating that it had been emitted just 900 million years after the Big Bang, meaning its photons had been traveling for over 13 billion years before arriving at our telescopes. This placed Earendel in a time close to what we believe is the era of the first stars, population 3. But what became of Earendel? Despite its light surviving the ages, the star itself is almost certainly long gone. A star's fate is governed by a single defining trait: mass. Mass determines a star's temperature, its luminosity, and most crucially, its lifespan. Stars like our Sun are middleweights massive enough to sustain hydrogen fusion in their cores, but not so massive as to live violently or die young. When the hydrogen in a sun-like star's core is exhausted, fusion continues in surrounding shells while the core contracts, heating up and triggering helium fusion. The star swells into a red giant before eventually shedding its outer layers into a planetary nebula, leaving behind a dense, inert white dwarf composed primarily of carbon and oxygen. These white dwarfs can persist for billions, perhaps trillions of years. But for more massive stars, the story ends with far more violence. Stars above about 10 solar masses experience successive stages of fusion, burning heavier and heavier elements in concentric shells. Ultimately, they reach iron, the fusion of which consumes energy rather than releases it. Without a fresh source of outward pressure, gravity takes over. The result is a supernova, a cataclysmic explosion that tears the star apart, sending enriched material flying into the interstellar medium. The core collapses into a neutron star, or if massive enough, a black hole, a region of space-time from which not even light can escape. And paradoxically, the more massive the star, the shorter its lifespan. These giants live fast, burning through their fuel at breakneck speed, their enormous energy output a sign not of endurance, but of fragility. While our sun is expected to endure for around 10 billion years, a 100 solar mass star may live for only a few million mere cosmic moments. So Arendelle, brilliant as it was, will have lived and died in a blaze of elemental violence, but it is the products of that death-heavy elements that make Arendelle's story so critical to our understanding of the cosmos. It was in the 1940s that astronomer Walter Baade proposed that not all stars are created equal. He observed subtle differences in stellar spectra between stars located in different regions of the Milky Way. Those in the spiral arm sites of ongoing star formation exhibited higher levels of heavy elements. Baade labeled these stars Population 1, the youngest generation enriched by the deaths of their ancestors. In contrast, stars found in the halo of the galaxy, those in globular clusters or drifting in the intergalactic outskirts, showed much lower metallicity. These older stars, dubbed Population 2, formed earlier in cosmic history from gas that had experienced less recycling through stellar deaths. But this raised a deeper question. If even Population 2 stars contained trace amounts of heavy elements, then there must have been a time before any such enrichment. A time when the universe was a clean slate composed almost entirely of hydrogen and helium, with just the faintest whisper of lithium and beryllium created during Big Bang nucleosynthesis. Theoretically, there must have been a first generation of stars. Stars formed before any enrichment forged from pristine cosmic gas clouds. These are the elusive Population 3 stars. Despite decades of searching, no Population 3 star has yet been conclusively observed. Arendelle's light, while ancient, still seems to bear the spectral fingerprints of some heavy elements, suggesting it is likely a Population 2 star. But what makes Population 3 so hard to find? The conditions of the early universe were drastically different from today. In modern star-forming regions like the Orion Nebula, heavy elements are abundant. These metals, through their electron configurations, enable gas clouds to cool efficiently by radiating away energy in the form of photons. This cooling is essential. It allows clouds to condense under gravity, forming dense cores that can ignite fusion. In the primordial universe, however, there were no heavy elements to assist in this cooling. Without metals, early gas clouds retained their heat, more stubbornly resisting collapse unless they were enormous. Only the most massive clouds, those with sufficient gravitational pressure, could overcome this resistance and compress to the point of nuclear ignition. As a result, theoretical models predict that Population 3 stars were likely huge, perhaps hundreds of times the mass of the Sun. Their size made them short-lived, dying in spectacular supernovae or collapsing directly into black holes. and their deaths seeded the cosmos with the very elements that would become the building blocks of future generations of stars, planets, and even life. But therein lies the observational challenge, population 3. Stars may have all vanished billions of years ago, their lifespans too brief for any to remain today. Their ancient light would be too dim, too diffuse to detect, unless magnified by the kind of gravitational lensing that revealed Arendelle, and even then, the alignment would have to be perfect. Still, astronomers haven't given up the James Webb Space Telescope, with its unprecedented infrared sensitivity, is now targeting deep fields of space peering farther back in time than ever before. By analyzing the chemical fingerprints of the earliest galaxies and stars, scientists hope to detect indirect evidence of population 3. Stars, perhaps by identifying supernovae with peculiar energy signatures or unusual abundance patterns in ancient gas clouds. And some are taking a different approach altogether. Stellar archaeologists, scientists who study ancient stars in the halo of our galaxy have identified ultra-metal poor stars, relics of the early cosmos that may have formed from gas enriched by a single population 3 supernova. These stars, though not population 3 themselves, may hold chemical records of their forebears. Ultimately, the discovery of a true population 3 star one completely devoid of heavy elements would be like finding the missing link in our cosmic ancestry. It would confirm our theories of early star formation and offer direct insight into how the universe transitioned from darkness to light. For now, though, population 3 remains a theoretical construct compelling, inevitable, and yet invisible. But perhaps in some untouched corner of the sky, one still lingers, an ancient ember burning against the black. Or maybe its light is already en route, a message from the dawn of time, just waiting to be caught by our outstretched instruments. Whatever the case, we will keep searching, because in that first generation of stars lies the beginning, not just of cosmic structure, but of us. Without population 3, there would be no carbon in our cells, no oxygen in our lungs, no planets to call home. They were the architects of the universe we now inhabit. And somewhere scattered across the deep time sky, they are still whispering their story, if only we can learn how to listen. The hunt for the first stars. More than 500,000 years ago, on the island of Crete, a peculiar version of a familiar giant once roamed. Unlike their towering relatives of the Ice Age, these mammoths stood no taller than a meter. In an isolated environment with scarce resources and few predators, gigantism became maladaptive. Evolution worked its quiet transformation, and thus insular dwarfism gave rise to the pygmy mammoth. Today, their bones are rare archaeological treasures, fragments of an evolutionary past that unfolded in isolation. In many ways, astronomers today find themselves on a similar quest. They are not searching for mammoths, but for the cosmic giants that once roamed the early universe, the very first stars, the elusive population 3. These primordial titans, born of pristine hydrogen and helium, lived fast and died young. Yet just like their mammalian counterparts, there's a hypothesis that smaller variants of these ancient stars may have existed and may still be among us. If such stellar pygmies formed early and lived long enough, they may have survived to this day, quietly orbiting in the distant halo of our galaxy, masquerading as ordinary stars. This is the central idea behind the modern-day astronomical pursuit known as stellar archaeology, the search for the last survivors of the universe's first generation. When the first stars ignited their nuclear fusion, lit up a universe that had known only darkness, but they did more than shine. They changed everything. In their hot cores, these stars fused hydrogen into helium and then into heavier elements, carbon, oxygen, magnesium, and beyond. When they died in spectacular supernovae, they seeded the surrounding cosmos with the ingredients for planets, atmospheres, and eventually life. But this enrichment was swift and efficient. In just a few million years, no region of the universe remained chemically untouched. The era of pristine star formation came to a rapid end. If we wish to understand the chemical history of the cosmos, if we want to learn how galaxies evolve and how elements are forged, then we must understand these first stars. Their existence marks a turning point between two fundamentally different epochs of the universe. But there's another motivation too, one that lies beyond data and theory: curiosity. The same deep human impulse that compels archaeologists to brush dust from ancient bones drives astronomers to trace faint light back to the birth of time itself. For decades, astronomers believed the search for population 3 stars was a hopeless endeavor. Their short lives made them unlikely candidates for survival into the modern era, but this assumption rested on another, that the first stars were all massive. Newer simulations suggest that while rare, smaller first-generation stars, those with masses below the Sun may have formed in the turbulent disks of primordial star clusters. If this is true, then these low-mass population 3 stars could have lifespans longer than the current age of the universe. They might still be here, hidden among the hundreds of billions of stars in the Milky Way. This idea, however, presents a daunting observational challenge. If any of these ancient stars have survived, they are exceptionally rare. We are looking for one in a billion, perhaps 1 in 10 billion. Worse still, these stars may no longer wear their original chemical coats. Over 13 billion years, they would have drifted through enriched environments, slowly accreting heavy elements onto their surfaces, effectively disguising themselves as younger stars. So, how do we find them? The answer, once again, lies in light. Spectroscopy, the study of starlight split into its component wavelengths, reveals a stellar fingerprint. The pattern of absorption lines tells us not only what elements are present in a star's atmosphere, but also their abundances. Population 3, stars formed from primordial hydrogen and helium, should exhibit no detectable traces of heavier elements. Their spectra should be devoid of the lines associated with iron, calcium, magnesium, and other metals. But surface pollution complicates things. A truly pristine star might still show faint metal lines if it has spent billions of years drifting through enriched interstellar gas. Fortunately, not all elements are equally easy to fake. Iron, in particular, is a robust tracer. Its lines are strong and difficult to mimic with surface contamination. For this reason, many surveys begin by measuring iron content as a proxy for metallicity. Stars with unusually weak iron lines are flagged as candidates for further study. And this is where stellar archaeology becomes a delicate, labor-intensive craft. Once promising candidates are identified, astronomers obtain higher resolution spectra to measure abundances of multiple elements. They then model the expected surface pollution for stars of a given age and trajectory, subtracting the contamination to infer the star's original composition. The hope is to find a star whose spectrum, once stripped of its disguise, reveals no metals at all. In 2013, astronomers made a breakthrough. A star labeled SMM03136708 was found with no detectable iron, an astonishing find. Detailed modeling revealed that it did contain small traces of other elements, likely produced by a single low-energy supernova. This wasn't a population 3 star, but its immediate descendant. Its chemical fingerprint told the story of one predecessor, a massive star that exploded and seeded just enough material to form one solitary child. We had not found a first star, but we had found its heir. To find an actual population 3 star, we must be even more precise. We must explore the galactic regions where time has moved the slowest. The Milky Way consists of three major components: the disk, the bulge, and the halo. The disk, home to our sun, is a dynamic metal-rich region teeming with young stars and ongoing star formation. The bulge, concentrated in the galactic center, is older but heavily obscured by dust and overcrowded with stars. The halo, by contrast, is sparsely populated and composed largely of ancient stars. It is here that astronomers have focused their search. The halo is a cosmic retirement home, a quiet space where ancient stars drift undisturbed. In this low-density environment, it is more likely that a pristine star, if one exists, could have survived intact. Yet even here, the camouflage problem remains. Polluted by time, these ancient stars may appear indistinguishable from younger ones unless we know exactly what to look for. Advanced simulations help here. By modeling how stars form and evolve in different chemical environments, astronomers can predict the detailed patterns we should expect in a true first star spectrum, even after accounting for surface contamination. The hunt then is part astronomy, part forensics. We are brushing away the cosmic dust that has settled over 13 billion years, searching for a star that was born before the universe had metals, before there were planets, before galaxies had taken shape. And as with archaeological excavations, each new find, even if not a pristine first star, provides clues. Each ancient spectrum is a relic, a piece of the puzzle. Ultimately, if we are to find a population 3 star in the Milky Way, it will not be a towering giant, but a cosmic pygmy, a small, faint relic of a bygone era. These survivors, if they exist, would rewrite our understanding of the early universe. They would confirm that even in the earliest days, the cosmos had diversity, not just in star size, but in fate. Yet the giants, the true behemoths of the cosmic dawn, may forever remain out of reach. Their light faded long ago. Their deaths seeded the cosmos with possibility, and their remnants lie scattered across time. If we are to learn their stories, we must turn not just to stellar archaeology, but to cosmic innovation, to new methods of inference, new ways of reading the scars they left behind. Their light may be gone, but their echoes in elements in stars and in us remain. Mammoths of the cosmos, tracing the giants that lit the early universe. What if one quiet evening, while scanning the familiar constellations in the night sky, you noticed a star was missing? Would you detect it one among thousands? In 2015, astronomers were confronted with this very mystery. A star once cataloged and known simply vanished. This object, designated N6946BH1, lay in a distant galaxy known as the Fireworks Galaxy. Prior to 2009, it had been a relatively unremarkable red hypergiant, roughly 25 times the mass of our sun. But something changed. In that year, it flared dramatically, brightening to over 1 million times the sun's luminosity. It burned with this furious intensity for several months. And then, nothing. No supernova, no fading remnant. The star had simply disappeared. Subsequent observations revealed only a faint infrared afterglow, insufficient to match any known supernova profile. Instead, astrophysicists proposed a more extraordinary explanation: the star had undergone a failed supernova. In this rare scenario, the core of the star collapses so violently that a black hole forms, directly bypassing the typical explosion and instead pulling the stellar material inward. The minimal outer layer of gas ejected just before collapse produces a faint signature, one far too dim for an ordinary supernova. If this interpretation holds true, N6946BH1 represents the first observational evidence of a black hole forming in real time without the fireworks we expected. Such an event had long been theorized to reconcile discrepancies in stellar evolutionary models. The rate at which massive stars form exceeds the observed frequency of supernovae. The implication: Some stars must die more quietly than our models had anticipated. This discovery has enormous consequences. It also opens a tantalizing window into the past, offering insight into the lives and deaths of the earliest stars, the so-called population 3 stars. These were the giants of the cosmic dawn, born from a primordial universe unpolluted by heavy elements. They were true stellar mammoths, immense, short-lived, and crucial to the evolution of everything that followed. Much like the terrestrial mammoths that once roamed Earth, these stars have left no direct descendants, and just as our knowledge of Ice Age fauna comes largely from fossilized remains and preserved DNA fragments, our understanding of population 3 stars must be reconstructed from the traces they left behind in radiation, in gravitational ripples, and in the chemical signatures they imprinted on their surroundings. The analogy with biological mammoths extends even further. Some extinct mammoth species preserved in Arctic permafrost still retain strands of DNA and even tufts of hair. These fragments have prompted discussions of de-extinction, using modern elephants as genomic scaffolds to potentially resurrect these ancient creatures. In astronomy, the conceptual equivalent is our study of hypergiant stars like Betelgeuse or UY Scuti, modern elephants from which we infer the properties of the long-lost mammoths of the early cosmos. Despite the similarities, there is one crucial difference: we will never observe the most massive population 3 stars directly. They have long since perished, their lives lasting only a few million years, yet they left behind unmistakable fingerprints through the radiation they emitted, the explosions they triggered, and the black holes they may have seeded. One of the most powerful tools we have to track these stellar giants is the 21-centimeter hydrogen line. Neutral hydrogen, unaffected by ionizing radiation, emits this radio wave signature due to a spin-flip transition in its electron-proton structure. But when UV photons from the first stars ionize hydrogen, they break apart the atom, eliminating the 21-centimeter signal in that region. The result is a universe peppered with holes in the hydrogen map regions where stars once blazed, leaving behind vast ionized bubbles. The cosmic map of 21 centimeter emission resembles Swiss cheese. The neutral hydrogen forms the solid cheese, and the ionized voids are the holes. Each hole represents the energetic influence of a first-generation star or black hole. The properties of these bubbles' size, shape, frequency tell us not only how many stars there were, but also how they lived and died. Mapping these bubbles is the task of advanced radio observatories like the Square Kilometer Array. Through its unprecedented sensitivity, the SKA is poised to reconstruct the timeline of the epoch of ionization, the era when the first stars and galaxies transformed the dark neutral universe into the luminous cosmos we see today. But the lives of these ancient mammoths didn't end in silence. Many died in dramatic explosions known as pair instability supernovae. These are unlike any supernova observed in the modern universe. In such stars ranging from 140 to 260 solar masses, gamma photons in the core spontaneously convert into electron-positron pairs, reducing the radiation pressure that holds the star up. This triggers a rapid collapse, followed by an explosive fusion of oxygen that completely unbinds the star. No remnant is left, not even a neutron star or black hole. All of the star's material is expelled into space, enriching its surroundings with heavy elements. Detecting such an explosion would be a cosmic milestone. The James Webb Space Telescope has the sensitivity to capture the light from these rare events, especially if the supernova is gravitationally lensed. However, such alignments are exceedingly rare. Nevertheless, even one confirmed detection would revolutionize our understanding of stellar nucleosynthesis and early cosmic evolution. There are other signs too. If two direct collapse black holes born from the collapse of massive first stars became gravitationally bound, they could merge, emitting gravitational waves detectable across the universe. Such signals are feeble due to their immense distance and age, but future missions like LISA, a space-based gravitational wave observatory, could detect them. LISA's design, 3 spacecraft separated by millions of kilometers, will allow it to detect the low-frequency waves emitted by massive black hole mergers. These mergers would provide key insights into the upper end of the population 3 mass distribution. Were these stars hundreds or even thousands of solar masses? Did they live long enough to form binaries? Did their collapse lead to the formation of the supermassive black holes now observed in the centers of galaxies? Modern astrophysics is attacking these questions from every angle, from indirect chemical signatures to high redshift supernovae, from 21 centimeter maps to gravitational wave backgrounds. The hunt is on. Each method is a different excavation tool. Some search for bone fragments, others for fossilized footprints. All strive to reconstruct the story of the earliest giants. These first stars played a pivotal role in shaping the universe. Their UV radiation ionized the intergalactic medium. Their supernovae seeded the cosmos with heavy elements. Their deaths may have spawned the first black holes, setting the stage for the growth of galaxies. They did all this in silence, in solitude, and with astonishing speed. And yet their legacy persists. The universe is forever marked by their brief but transformative existence. As we continue to observe the cosmos peering deeper into space and thus further into time, we move closer to the moment when darkness first gave way to starlight. That turning point when the universe lit its first candles remains one of the most profound in all of cosmic history. The search for the stellar mammoths is more than an astronomical pursuit. It is a journey to understand where light structure and chemical complexity began, and perhaps where our own story in its earliest form truly started. What would you see if the universe forgot to build stars around you? What would it feel like to drift in a place so vast and hollow that light itself seems to have given up? Can you imagine a void so immense, so unfathomably empty, that the very notion of existence feels like a myth? Close your eyes. Picture yourself floating alone in a super void, an immense sphere of darkness where the very fabric of the cosmos feels unfinished. There are no stars, no galaxies, no soft glow of clustered starlight to anchor your place in the universe. With the naked eye, or even the power of an amateur telescope, you see nothing. No Orion, no Andromeda, no comforting map of constellations we once used to navigate both oceans and imagination. To you, the universe would feel truly empty. And yet, this place exists. It is not fiction, but fact, known as the Boötes Void. This cosmic cavern spans 330 million light-years across a chasm so large the Milky Way could vanish into it millions of times over. Despite its gargantuan volume, roughly 1 million cubic megaparsecs, where we would expect thousands of galaxies to cluster and dance in gravitational spirals, astronomers have observed a mere 60 galaxies scattered like whispers in the dark, faint spiral, and blue echoing the birth cries of young stars forming in isolation. Astronomer Greg Aldering once remarked that had the Milky Way formed within the center of this void, we would not have discovered the existence of other galaxies until the 1960s. That's how barren, how deceptively silent this region of the cosmos is. Imagine if Earth lay on one edge of this void. The light from the opposite side would only just now be arriving, carrying stories from a time when amphibians still crawled through primordial swamps, millions of years before even the first dinosaur opened its eyes to the sun. The Boötes void, often called the Great Nothing, defies our expectations of cosmic structure. According to our understanding, the age of the universe places a strict limit on how large any coherent structure can be. No galaxy cluster, no cosmic filament, no void should exceed several tens of millions of light years in diameter. And yet here we are, confronted by a structure that shatters that threshold, a supervoid that challenges the very rules we thought governed the universe. Its presence tells us something, though. The few galaxies that do reside within it are not randomly strewn, but instead follow a linear, almost tubular pattern. It is as if we are seeing the fragmented ruins of a wall, a cosmic boundary crumbled between two adjacent voids. Individually, these voids make sense, but collectively, they form a structure beyond what cosmic evolution alone should allow. Even in this cosmic abyss, this supposed great nothing matter still finds a way to cling to structure, light still finds a way to be born. Yet to glimpse true darkness, to peer into the deepest recesses of time and space, we must look beyond even the Boötes void. We must travel not just across distance, but backward through time, to an epoch before stars, before galaxies, before light itself. This is the era cosmologists call the Cosmic Dark Ages. For nearly 200 million years after the Big Bang, though the universe possessed all the raw ingredients needed to forge stars, no star had yet ignited. There was no light, only cooling hydrogen-helium and the silent seeds of future galaxies. The darkness was not metaphorical, it was literal, total, and enduring. A silence so absolute that the cosmos itself seemed to be holding its breath. And so we must ask, why did the universe wait so long to turn on the lights? What does this long, unilluminated pause reveal about the galaxies we see today? How can we possibly understand an era where there was no light to guide us? From Copernicus, who displaced the Earth from the center of the solar system, to Hubble, who revealed our galaxy to be one among billions, the history of cosmology has been a series of humbling revelations. We are not the center of anything, not the solar system, not the galaxy, not even the universe. The deeper we look, the more we realize how small our place is, and how vast the mystery still remains. The edge of darkness, observing the threshold between light and night. In the annals of observational cosmology, few moments have marked a turning point as sharply as the Hubble Deep Field exposure of 1995. This historic event did not begin with grand discoveries or triumphs, but rather from skepticism, pressure, and a bold scientific intuition. The Hubble Space Telescope, the crown jewel of astronomical instrumentation, had endured a tumultuous debut. Its launch into low Earth orbit had been met with both optimism and public scrutiny, amplified when the first images returned from space were far from the clarity scientists had anticipated. Despite Hubble's mirror being one of the smoothest and most precisely ground optical surfaces ever created, a minuscule aberration less than 1/50th the width of a human hair resulted in devastating image blur. The collected photons failed to converge accurately, and the telescope's great promise seemed to unravel into failure. However, Hubble's low Earth orbit, which could have been a logistical limitation, became a saving grace. A crude servicing mission by NASA astronauts was able to correct the flaw through an ingenious optical fix, a series of small corrective lenses, not unlike those in a pair of glasses. With its vision restored to sharpness, Hubble was back in the game, but its credibility still needed defending. Under political pressure and scientific expectation, Robert Williams, the then director of the Space Telescope Science Institute, was allotted discretionary observing time hours he could spend observing anything in the cosmos. What he chose shocked his peers. Rather than direct Hubble's unprecedented sensitivity toward a known target, a star-forming region, a prominent nebula, or a supernova remnant, Williams decided to point the telescope at what was effectively nothing. A tiny, seemingly empty patch of sky in the northern hemisphere covering an area no larger than 1/30th. The diameter of the full moon was selected. To the human eye and to all previous telescopes, it was devoid of structure or light. There were no visible stars or galaxies. It was a celestial void. For 10 continuous days, Hubble gazed at this darkness. With each passing hour, its deep field camera gathered the feeble ancient photons arriving from the farthest recesses of the universe. This act of patience and vision culminated in the Hubble Deep Field, a single image that contained thousands of galaxies, each a sprawling collection of billions of stars suspended in space and scattered across time. It was an astronomical revelation. What had once seemed like emptiness was in fact a dense thicket of galactic forms, spirals, ellipticals, irregulars, red, blue, and everything in between. But this image was more than just a cosmic census. It was a temporal map. Every point of light captured was not only distant in space, but also in time. Due to the finite speed of light, observing faraway galaxies is equivalent to looking into the deep past. The farther away the galaxy, the longer its light has traveled, and the further back in time we are observing. Some of the galaxies in the Hubble Deep Field appeared as they were billions of years ago, close to the time when galaxies first began to form. To interpret this phenomenon with rigor, cosmologists conceptualize the observable universe as a set of concentric spherical shells centered on the observer. Each shell represents a greater light travel distance and therefore an earlier epoch. The light from our sun takes approximately 8 minutes to reach us, placing it in our innermost shell. The light from the Andromeda Galaxy, our nearest galactic neighbor, takes about 5 million years, carrying with it the image of that galaxy as it existed when early hominids like Homo habilis roamed the Earth. This ladder of light time continues outward. With advanced telescopes like Hubble and now James Webb, we can peer out to shells whose light began its journey just a few 100 million years after the Big Bang. These earliest visible galaxies, little more than red smudges, are some of the universe's primordial stellar systems. As feeble as these signals are, modern instruments allow us to dissect their light using spectroscopy. The same principles that govern the Doppler shift of a passing ambulance's siren apply to light. When a galaxy recedes from us, its emitted light stretches into longer wavelengths, a phenomenon known as redshift. Chemical elements emit light at known frequencies. When we observe their spectral lines shifted into the red end of the spectrum, we can quantify how fast the galaxy is moving away. Edwin Hubble, whose work underpins modern cosmology, famously discovered that the farther a galaxy is, the faster it is receding. This empirical relationship became foundational to the Big Bang model. In this way, redshift becomes a tool not only for measuring distance, but also for ordering galaxies chronologically. As we analyze deep field images, we are peeling away the layers of cosmic history, eventually arriving at the first luminous structures to emerge after the dark birth of the universe. The most recent deep field images from the James Webb Space Telescope offer an even sharper look into this past a single frame, covering a region of sky the size of a grain of sand, reveals thousands of galaxies, many dating back to a few 100 million years after the cosmic beginning. Yet there is a limit, a frontier beyond which even our most sophisticated instruments cannot penetrate. This is not merely a technological boundary, it is a fundamental limit of physics. Beyond a certain point, we arrive at a time before stars had ignited, before galaxies had formed, before there was any visible light at all. We call this epoch the Cosmic Dark Ages. To understand this profound darkness, one must return to the early radiation-dominated universe. Immediately following the Big Bang, the cosmos was a seething plasma of photons, electrons, and baryons. Light could not travel freely as it constantly scattered off free electrons, keeping the universe opaque. This state persisted until about 380,000 years after the Big Bang, when the universe cooled sufficiently for electrons to combine with protons and form neutral hydrogen atoms, a period known as recombination. With fewer free electrons to scatter photons, the universe became transparent for the first time. The radiation released at this moment, the cosmic microwave background, still bathes the universe today. However, although photons were now free to travel, the light emitted during recombination has been redshifted by the expansion of the universe. Originally a warm orange glow, it gradually stretched into the infrared and now into the microwave range. The universe cooled and visible light disappeared. The cosmic embers of creation dimmed into darkness. For nearly 200 million years, the universe entered a period devoid of any sources of visible light. The matter was too diffuse and too cool for nuclear fusion. There were no stars, no galaxies, and thus no new light. During this long night, another invisible actor played a critical role: dark matter. First identified indirectly by Vera Rubin and Kent Ford in the 1960s, dark matter's gravitational influence was needed to explain the unexpectedly high orbital velocities of stars within galaxies. According to Newtonian physics, stars orbiting at great distances from the galactic center should move more slowly. Instead, observations revealed that they maintained high speeds, implying the existence of unseen mass exerting additional gravitational pull. This mass, which does not emit, absorb, or reflect light, was termed dark matter. It is now estimated to comprise about 80% of the universe's total matter content. The behavior of dark matter is profoundly different from that of ordinary baryonic matter. While normal matter interacts through both gravity and electromagnetism, allowing it to cool by emitting radiation, dark matter interacts only via gravity. This means that as dark matter collapses under its own gravity, it cannot radiate away thermal energy. Without this cooling mechanism, gravitational contraction is arrested when the pressure from random thermal motion balances the inward pull of gravity. Consequently, dark matter structures form vast diffuse filaments and halos but never condense into stars or planets. During the cosmic dark ages, dark matter formed a hidden skeleton upon which the future large-scale structure of the universe would be built. The absence of visible light does not imply the absence of structure. The dark matter filaments formed a complex cosmic web with nodes of high density, forming halos into which baryonic gas would later fall. These halos provided the gravitational wells necessary to accumulate and compress gas, setting the stage for the first stars. But for this to happen, the gas itself had to cool, condense, and eventually trigger fusion. Unlike dark matter, normal gas clouds can cool through atomic interactions. As atoms collide, electrons become excited to higher energy levels. When they relax back to their ground states, they emit photons, carrying away energy and reducing the internal pressure. Over time, this radiative cooling allows the cloud to collapse further, increasing in density until the conditions for nuclear fusion are achieved. In this way, the first stars, known as population 3 stars, were born. These stars were likely massive, short-lived, and composed almost entirely of hydrogen and helium, lacking the heavier elements synthesized by later generations of stars. Detecting these primordial stars directly remains one of the most elusive goals in astrophysics. Their faintness, great distance, and short lifespans conspire to hide them from even our most sensitive telescopes. Nevertheless, their indirect fingerprints may yet be found in the chemical composition of later stars, in the reionization history of the intergalactic medium, and in the subtle distortions they imprint upon the cosmic background light. And so we return to the present. Our telescopes stationed above the Earth's atmosphere, armed with mirrors and spectrographs, continue to gaze into the void, not out of despair, but out of curiosity. The darkness is not empty, it is filled with structure, with memory, with signals stretched thin by time and space. From the glowing fog of recombination to the cool embers of the cosmic microwave background, from the hidden scaffolding of dark matter to the first glimmers of starlight, the universe reveals itself not in brightness but in persistence. As we trace the universe backward, peeling away the layers of time, we approach a limit beyond which no light was ever cast. And yet the questions persist. How did the universe first ignite? What mechanisms seeded the galaxies and clusters? We now see what lies beyond the observable horizon. These questions remain unanswered but not unreachable. The edge of darkness is not the end of knowledge, it is the beginning of insight. It is the place where physics, imagination, and the hunger for understanding converge, where the silence of the cosmos speaks in wavelengths too faint to hear, but whose message is clear. Keep looking. The hidden universe, illuminating cosmic darkness through hydrogen's whisper. On the afternoon of May 6, 1937, an enormous symbol of engineering pride and technological ambition descended toward its mooring mast in Lakehurst, New Jersey. The German airship Hindenburg, a leviathan of the skies and a marvel of intercontinental air travel, suddenly erupted into flames. The hydrogen that lifted it, a gas prized for its lightness, ignited with terrifying speed, engulfing the vessel in a fiery inferno, witnessed by horrified onlookers. Though most on board survived due to the airship's proximity to the ground, the tragedy spelled the end of the hydrogen-fueled airship era. A simple element, hydrogen, composed of one proton and one electron, had unleashed catastrophic energy when given the right mix of air and a spark of ignition. This elemental simplicity is deceptive. Hydrogen is odorless, invisible, and under the right conditions, violently reactive. In the case of the Hindenburg, the combustion of hydrogen ended an age of flight. But the power contained in the atom is not limited to chemical combustion. In nuclear physics, it serves as a gateway to vastly greater energies. The detonation of atomic bombs in Hiroshima and Nagasaki illustrated the terrible potential of fission. But the true apex of destructive energy lies in hydrogen fusion. Thermonuclear weapons based on the fusion of hydrogen nuclei, far more powerful than fission bombs, have only been tested in controlled detonations, never unleashed in war. Ironically, the same scientific curiosity that unlocked the hydrogen bomb also illuminated the stars. Many physicists who developed nuclear weapons were simultaneously probing the processes that power the cosmos, and it was hydrogen again that held the key. Yet while hydrogen's role in stellar fusion and weaponry occupied some minds, a quieter revolution was unfolding within astronomy. The focus of this revolution was not devastation, but discovery. John Oort, a preeminent Dutch astronomer, had already revolutionized our understanding of the Milky Way by showing that the Sun was not its center, but merely a peripheral resident located about 30,000 light-years from the galactic core. His work had confirmed that the Milky Way rotated like a massive spiral, and he became one of the most respected figures in the field. But by the early 1940s, war had disrupted European science. Oort, having protested the Nazi regime's dismissal of his Jewish colleagues, retreated from public academic life. Yet in isolation, he was not idle. The need to understand the true shape and extent of our galaxy continued to stir his scientific instincts. Oort's challenge was formidable. The Milky Way is a dusty system. Optical telescopes, which rely on visible light, are significantly hampered by interstellar dust that absorbs and scatters light. A comprehensive map of our galaxy would require seeing through this veil. The solution Oort believed lay in detecting radio waves, which possess much longer wavelengths and are largely unaffected by dust. But for this to work, the interstellar medium, the gas and plasma filling the galaxy, would need to emit radio signals detectable by Earth-based instruments. A breakthrough came in the form of a smuggled issue of the Astrophysical Journal that described potential methods of detecting radio emissions from space. Oort realized that hydrogen, which made up most of the interstellar medium, might provide the signal he sought. But the emission would need to be both widespread and physically plausible to detect. He tasked his student Hendrik Christoffel van de Hulst with identifying a suitable spectral line from hydrogen-1 that could serve as a beacon in the radio domain. Van de Hulst approached the problem with diligence, exploring the quantum mechanical behaviors of the hydrogen atom. In quantum terms, even the hydrogen atom's simplest structure harbors complexity. While most transitions involve electrons leaping between discrete energy levels, there exist subtler transitions hidden within those levels. One such transition is the hyperfine spin-flip transition. In this phenomenon, an electron orbiting a proton changes its spin orientation from parallel to anti-parallel. The energy difference between these two configurations is minute but real. When an electron flips to the lower energy state, it emits a photon with a frequency of precisely 14204 EHz, equivalent to a wavelength of 21 centimeters. This emission lies firmly within the radio band, making it an ideal target for radio astronomy. Van de Hulst published his theoretical prediction in 1944, suggesting that this 21 centimeter hydrogen line could revolutionize our understanding of the Milky Way. The challenge, however, was daunting. The spin-flip transition is extraordinarily rare. The spontaneous transition of a single atom may occur only once in several million years. To detect such a faint signal would require immense quantities of hydrogen, far more than anyone had yet confirmed in the galaxy. Skepticism was understandable. Many doubted that the universe held enough neutral hydrogen to make the 21 centimeter line detectable at all. Nevertheless, Oort pressed on. Using salvaged components from wartime German radar equipment, he attempted to build a radio detection system, but he was no electrical engineer and the project stalled. Meanwhile, across the Atlantic, a team at Harvard, led by physicist Edward Purcell, had independently read Van de Hulst's paper and taken a keen interest. Purcell, whose background lay in nuclear magnetic resonance, saw an opportunity to apply his expertise in radio detection. He enlisted his graduate student Harold Doc Ewan, whose knowledge of radar technology proved crucial. Ewan constructed a horn antenna, essentially a hollow metal structure shaped to direct radio waves into a receiver using basic materials, copper-plated plywood, and campus electronics. This antenna, installed through a fourth-floor laboratory window, became the first successful apparatus to detect the elusive 21 centimeter line on a quiet Easter morning in March 1951. The experiment worked. A distinct spectral line at 1420 MHz was observed, proving the existence of vast hydrogen reservoirs in the Milky Way. News of the success quickly reached Europe, and a collaborative scientific dialogue was born. The Americans shared the technical expertise needed to construct and calibrate radio receivers, while the Dutch provided the astrophysical framework that made sense of the findings. This transatlantic partnership catalyzed the field of radio astronomy, allowing astronomers to build detailed maps of hydrogen distribution throughout the galaxy. More than that, they could now measure not only where the gas was, but also how it was moving. By examining the redshift and blue shift of the 21 centimeter line, astronomers could determine the radial velocities of hydrogen clouds. These observations confirm that the Milky Way was a rotating spiral with arms that could be traced far beyond the reach of optical light. The implications for galactic astronomy were profound, but the significance of the 21 centimeter line extends far beyond our local spiral. The same principles can be applied on cosmological scales. Hydrogen was the most abundant element produced in the Big Bang, forming the vast majority of normal matter in the early universe. Before galaxies, before stars, before planets, the universe was filled with diffuse clouds of neutral hydrogen gas. Much of this gas still exists today, and the hyperfine transition remains a tracer of its distribution. In particular, the 21 centimeter line offers a window into one of the most enigmatic periods of cosmic history, the cosmic dark ages. After the universe became transparent, following recombination, roughly 380,000 years after the Big Bang, there were no luminous objects to emit visible light. The photons from recombination gradually redshifted into the microwave regime, becoming the cosmic microwave background. For hundreds of millions of years, the universe remained dark in the optical spectrum, filled with hydrogen gas and dark matter, but devoid of stars. Yet, even during this period, structure was forming. Dark matter, which interacts gravitationally but not electromagnetically, began to collapse into filaments and halos. The baryonic hydrogen gas followed, drawn in by gravity, settling into the gravitational wells created by dark matter. As these gas clouds cooled and contracted, the conditions for star formation began to emerge. But to the human eye or any optical telescope, this process was invisible. The universe was still dark. Herein lies the power of the 21 centimeter line. Unlike light from stars, which did not yet exist, the spin-flip transition of hydrogen could still occur. While individually rare, the sheer volume of hydrogen in the early universe ensures that the signal, when observed across cosmic distances, becomes statistically significant. By tuning radio telescopes to the redshifted 21 centimeter line, astronomers can detect the distribution of hydrogen across different epochs, tracing the evolution of matter long before the first starlight. Modern radio telescopes, such as the Square Kilometer Array under construction, are designed to take advantage of this fact. They aim to create three-dimensional maps of hydrogen distribution, effectively watching the universe evolve from darkness to light. These observations will not only pinpoint the locations where the first stars formed, but also help refine models of cosmic inflation, dark matter behavior, and the initial conditions of structure formation. The 21 centimeter line, then, is more than a spectral signature. It is a cosmic thread linking the present to the past, the luminous to the unseen. Through it, we can observe the quiet gathering of matter during the Dark Ages, when the universe was laying the scaffolding for galaxies, stars, and ultimately life. In retrospect, the hydrogen atom, simple though it may be, has proven to be one of nature's most eloquent storytellers. From the fiery destruction of an airship to the ignition of thermonuclear reactions, from the blazing cores of stars to the near-silent whisper of spin-flip transitions, hydrogen reveals itself across every scale. It is the most ancient of elements forged in the first few minutes of the universe, and it remains our most powerful tool for deciphering the cosmos. And so the universe was never truly dark. It was simply speaking in a different language, one that required new instruments, fresh insight, and a longer wavelength. The 21 centimeter line was the translator, the beacon, the whisper in the silence. Through it, we continued to learn that even in the deepest void there is form. In the darkness there is structure. The hidden universe is not empty. It is waiting to be heard. Let there be light, reconstructing the universe's path out of darkness. The deep ocean, Earth's largest and most enigmatic habitat, provides us with a terrestrial analogy for the cosmic darkness that once enveloped the early universe. As one descends beneath the sunlit surface of the sea, the light diminishes with increasing depth. At just 10 meters, the warm hues, reds, oranges, and yellows are absorbed, rendering the underwater world increasingly blue and green. By 50 meters, much of the visible spectrum has been swallowed by water, and the world is cast in an eerie monochrome. At 200 meters, one enters the twilight zone, a realm populated by bioluminescent creatures that have evolved to generate their own light. By 300 meters, one is immersed in the ocean's true darkness, an environment hostile to human perception yet teeming with life, adapted to this lightless realm. The metaphor is apt, for the early universe too was a place of darkness, not devoid of activity, but veiled from our visible senses. In the cosmic timeline, a similar descent into darkness followed the initial brilliance of the Big Bang. After the universe cooled from its initial hot plasma state and atoms formed during recombination, the cosmos entered a prolonged period of darkness. This era, known as the Cosmic Dark Ages, lasted for hundreds of millions of years. During this time, the universe was devoid of luminous sources, no stars yet shone, and no galaxies yet burned. And yet, like the deep ocean, the darkness was not synonymous with emptiness. Invisible to the human eye and to optical telescopes, the universe was already undergoing gravitational assembly beneath the shroud of blackness. The architecture of structure formation had already been laid. The gravitational influence of dark matter had begun to assemble filaments and halos, forming a vast cosmic web into which neutral hydrogen, comprising the bulk of ordinary matter, began to accrete by approximately 200 million years after the Big Bang. These dense hydrogen pockets had collapsed under their own weight to the point where fusion could be triggered. In doing so, the first stars ignited, and with them the first starlight broke the cosmic darkness. From every direction across the expanding cosmos, the first sources of light flickered to life. These were likely massive, short-lived population 3 stars, composed almost entirely of hydrogen and helium and devoid of heavier elements. Yet despite their brilliance, these early stars were not immediately able to flood the universe with light. The space between stars remained filled with vast amounts of neutral hydrogen, which readily absorbed specific wavelengths of radiation, particularly in the ultraviolet and optical bands. Much as ocean water absorbs light in the red and blue wavelengths, the surrounding hydrogen gas acted as an opaque veil that muffled the newborn light. An observer at this time might witness stars shining, but with their light dimmed and scattered, their spectra marred by characteristic absorption lines, specifically the Lyman alpha transition, and others where hydrogen absorbs at well-known visible wavelengths. The effect would not have been a total darkness, but a spectral tinting light filtered and shaped by its medium. The appearance of light did not therefore signal an immediate end to the Dark Ages. Rather, it marked the beginning of a new cosmic transformation, the epoch of Ryanization. During this epoch, the ultraviolet radiation from the first stars and later from the first galaxies began to ionize the neutral hydrogen that pervaded space. To understand this process, it is important to recall the atomic physics of hydrogen. In the Bohr model, the hydrogen atom consists of a proton orbited by an electron. When a photon carrying energy equal to or greater than 136 electron volts interacts with this atom, it can ionize it, freeing the electron from the proton and converting the atom into an ionized plasma. Following the Big Bang, the universe was too hot for neutral atoms to exist, and all matter was in the form of plasma. It was only after cooling for hundreds of thousands of years that electrons and protons combined to form neutral hydrogen, ushering in the dark ages. Now, with the advent of the first star's photons with energies exceeding the ionization threshold, began to reverse this process. Each luminous source created a local bubble of ionized hydrogen, a transparent region through which light could travel more freely. Initially, these bubbles were isolated and surrounded by darkness, but over time, as more stars and galaxies formed, the bubbles expanded, began to overlap, and eventually percolated through the intergalactic medium, transforming the universe from opaque to transparent once more. This global reionization of the universe was not the result of individual stars alone. Although population 3 stars contributed to the early phases of reionization, their short lifespans and limited ionizing output suggest they could not have completed the process alone. Instead, it was the first galaxies harboring longer-lived population 2 stars' massive star-forming regions and potentially active galactic nuclei that provided the sustained ionizing radiation necessary to reionize the cosmos. By about 1 billion years after the Big Bang, the reionization process was largely complete, and the universe became once again transparent to ultraviolet and visible light. Photons could travel across vast distances without being absorbed, and the large-scale structure of the universe could be observed in the way we experience it today. However, the details of this transformation remain elusive. The Dark Ages and the Epoch of Reionization represent a missing chapter in the cosmic narrative. A few galaxies from this time have been observed, dim ancient sources detected at extreme redshifts, but they are sparse to reconstruct a coherent picture of this era. From such a thin sample would be like reconstructing all of human history from a single archaeological artifact found every few centuries. The desire to peer into this mysterious epoch was a primary motivation for the development of the James Webb Space Telescope, launched on December 25, 2021. Whereas the Hubble Space Telescope operates primarily in the optical and near-infrared bands, JWST was designed to probe much further into the infrared. This distinction is critical due to the expansion of the universe. Light from distant galaxies is redshifted, its wavelength stretched such that photons originally emitted in the ultraviolet or optical range arrive at Earth in the infrared. Hubble's instruments, while powerful, are limited in their ability to detect these heavily redshifted signals. JWST, by contrast, can detect galaxies whose light has redshifted entirely out of the visible spectrum. Within its first year of operation, JWST succeeded in detecting some of the most ancient galaxies ever observed, with estimated formation times just 350 million years after the Big Bang. Yet even JWST has limitations. While it can observe further than any previous telescope, its field of view is small and its resolution constrained by its mirror size. Moreover, it is not equipped to see the earliest stages of the Dark Ages or to map the reionization process in its full complexity. To push further to capture the moment when the first hydrogen atoms were reionized, we must turn to an entirely different part of the electromagnetic spectrum, the radio band. As we journey backward in time, observing galaxies at ever greater redshifts, we simultaneously confront a paradox. The farther we look, the more of the universe we see per unit of sky area, but the lower our spatial resolution becomes individual stars, and even individual galaxies vanish into the statistical noise of unresolved light. To see structure on these large scales, we must observe phenomena that are spread broadly across space and time. This is where the 21 centimeter line predicted by Van de Holst and discussed earlier becomes essential. As described, the 21 centimeter hyperfine transition of neutral hydrogen occurs when the spin orientation of the electron and proton in a hydrogen atom change from parallel to anti-parallel. This transition releases a photon in the radio part of the spectrum with a wavelength of 21 centimeters and a frequency of 1420 MHz. Though rare, the immense quantity of neutral hydrogen in the early universe makes this transition statistically significant over cosmic volumes. Critically, the presence or absence of the signal can trace the progress of ionization. In regions where hydrogen remains neutral, the 21 centimeter emission persists, but in ionized regions where electrons and protons no longer form bound atoms, the signal disappears. Thus, during reionization, the universe begins to resemble a cosmic Swiss cheese, with neutral hydrogen representing the solid structure and ionized bubbles representing the holes. By mapping these patterns, astronomers can infer the size, shape, and evolution of the ionizing sources, be they first stars, galaxies, or black holes. The signal offers a three-dimensional view of the invisible universe, providing not only spatial but also temporal information thanks to the redshift dependence of the wavelength. Detecting the 21 centimeter signal from the epoch of reionization is one of the most ambitious goals in contemporary astronomy. The challenges are formidable. The signal is faint, so faint that it is overwhelmed by radio noise from our own galaxy, from Earth-based sources, and even from distant quasars. Extracting the 21 centimeter signal requires instruments of unprecedented sensitivity situated in radio quiet zones and equipped with advanced signal processing algorithms. Projects like Hera-Lofar and the upcoming SKA are designed specifically to overcome these challenges. Their success will provide a definitive timeline of reionization, reveal the properties of the first light sources, and perhaps even detect primordial black holes. And so the phrase, "let there be light," acquires new meaning in the cosmological context. The universe did not flip a switch from darkness to illumination, rather it transitioned gradually through complex, overlapping processes. Light was born, struggled to escape, and slowly carved paths through the opaque hydrogen fog. The first stars kindled the cosmic dawn, but the light they emitted was absorbed, reprocessed, and shaped by their environment. Only after 1 billion years of growth, radiation, and transformation did the universe become transparent once more. Even now, we are only beginning to uncover the full extent of this transformation. The Dark Ages and the epoch of reionization remain a frontier in our understanding, an interval that shaped everything that followed, yet still shrouded in mystery. But with every new instrument, every new signal, we peel back the layers. We listen for hydrogen's whisper in the radio spectrum, decode its interaction with early starlight, and search for the moment when the cosmic night began to fade. And so we ask, is it truly possible to find the signal of reionization and illuminate the Dark Ages? The answer lies not only in better telescopes, but in our persistent curiosity. For even in darkness, the universe leaves traces. And when we tune our ears to the right frequencies, we find that the cosmos was never silent. It was always preparing to speak. The signal listening to the universe's silent dawn. Imagine yourself standing under the searing sun in the heart of the Australian outback. All around is a parched and ancient landscape, an expanse of ochre earth punctuated by sparse, withered vegetation. The air shimmers with dry heat. No rivers flow, no clouds break the sky. Yet this land, seemingly inhospitable to humans, sustains other forms of life. Sheep graze quietly. Cattle meander across the dust. They inhabit this terrain differently, not just physiologically, but perceptually. For them, this land is not the red and gold of our human vision, but a landscape shaped by different wavelengths of light, processed by different kinds of eyes. Biological vision systems vary dramatically across the animal kingdom. Humans with our red, green, and blue cone cells perceive the world in a narrow slice of the electromagnetic spectrum, what we call visible light. But this is only a fraction of what exists. Cattle and sheep lack the ability to detect red entirely. Snakes, though color deficient, can sense infrared radiation, a capacity that aids them in tracking warm-blooded prey. Scorpions, astonishingly, can both detect ultraviolet light and fluoresce under its illumination. Nature is filled with such diverse perceptual tools. Unlike any other species, however, humans have transcended our biological limitations by constructing artificial extensions of our senses. In mimicking nature's diversity of perception, we have invented instruments that detect ultraviolet, infrared, X-ray, and critically radio waves. In doing so, we did not simply build new tools of perception, we developed entirely new modes of communication. What began as terrestrial radio, an attempt to broadcast sound and images, quickly became something far more profound. By accident and intention, we began detecting the faint whispers of the universe itself. In the process, a new discipline was born, radio astronomy. By tuning our instruments to the longest wavelengths of the electromagnetic spectrum, we began to detect radiation, not just from other rooms or cities, but from planets, stars, galaxies, and the earliest moments of cosmic history. It was through these technological eyes that humanity found its way into the electromagnetic realm, otherwise inaccessible to biological life. It is deep in the Australian outback, one of the quietest radio environments on Earth, that one of the most consequential developments in the study of the early universe unfolded. Here, far from the noise of cities in the Murchison region of Western Australia. A desert covering nearly 50,000 square kilometers, with only about 100 inhabitants. A seemingly unassuming radio antenna detected something extraordinary. The instrument known as edges stands in stark contrast to the massive dishes and gleaming optics we typically associate with astronomy. It is a modest ground-based radio antenna designed to do one thing: detect the red-shifted 21-centimeter signal from neutral hydrogen gas that pervaded the early universe during the cosmic dark ages and the subsequent epoch of rionization. These hydrogen atoms formed after recombination and before the ignition of the first stars emit radiation at a characteristic wavelength of 21 centimeters due to the hyperfine transition of the hydrogen atom's ground state. But as the universe expanded, these photons were stretched, redshifted, so that today they arrive at Earth with wavelengths between 1 and 2 meters, depending on their origin epoch. EDGES was designed to detect these photons not by imaging them as a traditional telescope would, but by measuring their collective brightness. Temperature, a global signal that provides an averaged view of hydrogen gas across cosmic time. It listens passively, its human operators often hundreds or thousands of kilometers away. The experiment operates like a celestial thermometer, scanning across radio frequencies to search for faint spectral dip signatures of interaction between hydrogen and the earliest radiation sources. In 2018, EDGES made a startling announcement. After years of careful calibration, noise modeling, and data analysis, the team reported the detection of an absorption feature at a frequency corresponding to redshift 17, or roughly 180 million years after the Big Bang. This detection, if confirmed, would mark the earliest direct evidence of the first stars, a cosmological milestone tantamount to discovering a birth certificate for stellar light. However, the implications of the signal extended beyond its timing. The depth of the absorption feature was twice as large as predicted by any standard cosmological model. In essence, the signal suggested that the hydrogen gas of the early universe was significantly colder than existing theory allowed. The discrepancy sent shockwaves through the cosmology community. At the heart of the puzzle lay the physics of the 21 cm line. The absorption of background photons at this wavelength depends on the spin temperature of hydrogen, which in turn is influenced by the kinetic temperature of the gas and the radiation field present. A deeper absorption trough implies that the hydrogen was either much colder than expected or that the background radiation field was much brighter. Both possibilities were unanticipated. One line of interpretation suggested a radical solution. Perhaps dark matter, long assumed to be non-collisional and thermally inert, could interact, however weakly, with normal baryonic matter. In this hypothesis, collisions between dark matter particles and hydrogen atoms would transfer kinetic energy, cooling the gas beyond standard expectations. If true, this would represent a fundamental shift in our understanding of dark matter with profound implications for particle physics and cosmology. The possibility electrified the field, but scientists proceeded with caution. Extraordinary claims demand extraordinary evidence, and the sensitivity of the EDGES experiment made it susceptible to contamination from terrestrial and galactic radio noise. The signal detected was incredibly faint, many orders of magnitude weaker than foreground radio emissions from our own Milky Way galaxy. Extracting the desired signal required complex modeling and subtraction techniques. Could the observed dip be a result of unmodeled instrument noise? Was there an unrecognized astrophysical foreground? Was it an artifact of calibration? To verify the result, independent confirmation was essential. A range of follow-up experiments soon emerged. In India, the SARAS experiment placed an antenna on a floating platform in a lake to minimize ground reflections and environmental noise. Its analysis, however, failed to reproduce the deep absorption feature reported by EDGES. While SARAS did not conclusively disprove the detection, its inability to corroborate it cast doubt. The field, always driven by data, began to retreat from the more exotic interpretations. The initial theories invoking dark matter-hydrogen interaction gave way once again to methodological scrutiny. Perhaps the signal was a systematic artifact, or perhaps the models of galactic foregrounds were insufficient. The return to conservatism was not defeat, it was scientific self-correction. And yet the potential insight gleaned from even the possibility of the EDGES result had already reshaped priorities in observational cosmology. Despite the controversy, EDGES had achieved something critical. It had galvanized the global scientific community to take the 21 cm cosmological signal seriously. Across the Murchison outback, other instruments were already listening. The Murchison Wide Field Array, comprised of hundreds of bow-tie-shaped antennas, had been probing the structure of the early universe through interferometric imaging, searching not for global signals, but for spatial fluctuations in the 21 cm line caused by the patchy nature of rionization. The local indigenous Wajari Yamaji people, stewards of the land, have poetically described the MWA as the ear that listens to the sky. Now, the Murchison site is preparing for the most ambitious project in the history of radio astronomy, the Square Kilometer Array. When complete, the SKA will consist of over 130,000 antennas distributed across the Australian desert. It will have the sensitivity to detect an airport radar from 10 light years away, and will be capable of mapping the epoch of rionization and the tail end of the cosmic dark ages with unprecedented resolution. And yet even the quiet Murchison region is not immune to interference. Human radio transmissions, satellite communication, and atmospheric disturbances continue to challenge ultra-sensitive observations. The ultimate destination for uncontaminated cosmology may lie beyond Earth entirely. Plans are already underway to deploy radio antennas on the far side of the Moon, a location naturally shielded from Earth's radio noise. There, in the permanent radio silence beneath the lunar regolith, astronomers hope to finally detect the primordial signal in its purest form. The pursuit is not merely technical, it is philosophical. The universe was dark for nearly 200 million years, not because nothing was happening, but because our instruments and senses were not attuned to its language. To optical eyes, the early cosmos appears blank, devoid of structure or meaning. But to a properly tuned antenna, the sky becomes alive with history. The 21-centimeter line, faint, elusive, and ancient, carries with it the tale of hydrogen clouds, cooling, collapsing, and forming the first stars. It chronicles the transition from plasma to atoms, from darkness to light, from silence to symphony. The EDGES experiment, despite its debated result, opened a new chapter in our exploration of the universe's earliest epochs. It reminded us that even in apparent silence, the universe has a voice. And now, with every new generation of radio instrument, we are learning how to listen more carefully. The Dark Ages were never truly dark, not to the sky itself, nor to the photons that have traveled billions of years to reach us. They were simply waiting for the right kind of eye.